Welcome to the second course on reliable distributed algorithms. This course is a continuation of the topics discussed in Reliable Distributed Algorithms Part 1. In Part 1, we covered a number of basic topics in distributed algorithms. These included formal models of asynchronous distributed systems, the event-driven programming model we needed for expressing distributed algorithms, how to specify distributed abstractions in terms of safety and liveness properties. We also introduced the concepts of failure detectors and reducibility and equivalence between various distributed abstractions. We then covered a number of reliable distributed services. These include various forms of reliable broadcast, distributed shared memory, and stronger consistency models, and the single value consensus problem and the associated Paxos algorithm for solving it in the partially asynchronous system model. The material of this part will be available for you as a reference material throughout Part 2. The intention of Part 2 is to introduce you to more advanced and practical material that is commonly used when building today's reliable distributed systems. We have numbered the lectures as continuation of the first course, which ended in Lecture 9. Lecture 10 is on replicated state machines and the problem of agreeing on a log or a sequence of commands. After briefly reminding you with a single value consensus, we define the problem of agreeing on a sequence and call it sequence consensus. We review the single value consensus algorithm and modify that algorithm to define a generic sequence Paxos algorithm that satisfies the specification of sequence consensus. We prove the correctness of the algorithm based on the original Paxos proof. This algorithm, although correct, is not efficient. Our goal is to get a very efficient algorithm that is used to implement replicated state machine. This algorithm is based on a leader that controls the order of sequence of commands, but we need to design a new leader election algorithm that is suitable for leader-based sequence Paxos. We call this leader election algorithm the Ballot leader election. The first week ends with a programming assignment on the Ballot-based leader election algorithm. The second week is devoted to the leader-based sequence Paxos algorithm. This algorithm is developed by a form of stepwise transformation of the generic sequence Paxos algorithm. Each step preserves the correctness of the original algorithm but improves its efficiency. This really aids understanding of the resulting final algorithm. As you will see, the final algorithm is very efficient and can be completely specified in 2 slides. This week ends also with a programming assignment on the leader-based sequence Paxos. In the third week, we are going to have 2 lectures. Lecture 12, we extend the leader-based sequence Paxos algorithm to work in the fail recovery model. In this model, correct processes may fail and recover a finite number of times. As you will see, we only need minor extensions to make the leader-based sequence Paxos work in this model. Equipped with the knowledge that we have gained so far, we end this lecture by describing the popular raft algorithm for sequence or log consensus. Lecture 13 covers dynamic reconfiguration of replicated state machines that are based on leader-based consensus algorithms. either sequence Paxos or Raft. By dynamic reconfiguration, we mean changing the set of processes participating in the replicated state machine without interrupting the service. And this ends the third week. In the fourth week, we cover some distributed algorithms that use time and physical clocks. It turns out that we can develop more efficient algorithms for some distributed abstraction by using local physical clocks in the asynchronous model. And sometimes we achieve certain properties that are not possible to achieve in a pure asynchronous model. We have two lectures. In lecture 14, we cover a least-based leader election algorithm that uses local physical clocks. We show that this algorithm improves the efficiency of certain operations in replicated state machines. In lecture 15, we introduce the notion of interval clocks, where the real value of time is guaranteed to be within a specified interval provided by the physical interval clock. We use interval clocks to design a more efficient, linearizable read-write distributed shared memory. Interval clocks are used in Google data centers to implement distributed databases. The last week is devoted to the topic of weaker consistency model. This week is presented by three guest lecturers: Peter van Rooij, Christopher Mikkeljohn, and Annette Pinoza. Lecture 16 covers the topic of relaxed consistency and conflict-free replicated data types. Distributed systems that require strong consistency models like linearizable or sequential consistency will suffer from unavailability under network partition, and can also suffer from inefficiency if the distributed system is geographically distributed with long delays between the sites. This lecture offers one possible solution, which is designing most of these services of the distributed system based on a form of monotonic data types that tolerate latency. This lecture covers conflict-free replicated data types, CRDTs, LASP, a programming platform for composing CRDTs, Antidote, a causal transactional database based on CRDTs. We end the technical material by a short overview of real systems using the concepts and algorithms presented in this course. The software used for programming assignment in this course is the Scala-based Compex. This was used also in part 1. It is an event-driven component middleware that is hosted in the programming language Scala. You will have 2 programming assignments during the first 2 weeks. One on ballot leader election, and the other on leader-based sequence Paxos. We will also have weekly graded quizzes. All should be delivered by the end of the course. There is no final exam in this course. To pass the course with full point, you need to do the graded quizzes and deliver the programming assignments. We will be available in the discussion forum to assist you throughout the course. So let us start.